Okay, guys. I just wanted to start off by reminding you that I'm sorry I didn't remind you this on Wednesday. It just slipped my mind, on Monday that is. Just slipped my mind that you guys had your milestone 2 due on Monday, which I trust you guys all submitted. I just forgot to remind you. Oh, it got moved. So that I didn't forget then. I forgot. Okay. I forgot twice, so they cancel each other out. So it's due on Friday, is that right? Okay. Somehow we didn't. So we just didn't update the website, is that right? That's all that's happened? Okay. Well, that's good. So your milestone 2 is due on Friday. I'll say this anyways now because it's a good reminder. So when you submit your milestone 2, you're going to submit it to EasyChair. The instructions are down here. Right here, submission instructions. So EasyChair is a website for running conferences, and we've been doing this in this class for several years. Now that you submit your milestone 2 to EasyChair, I believe you also submit a copy to your TA mentor. It says in the instructions, so just follow them. But the copy you submit to EasyChair is you take your names off, so it's anonymized. And the way that we do this is that everybody in the class gets assigned as a reviewer to somebody else's milestone 2. And depending on the number of project groups and the number of people in the class, we're going to try to get like 2 or 3 reviews, probably minimum of 3 reviews per milestone report, milestone 2. So I don't know exactly how many that you'll be assigned, but it'll be a small number, a very small number. Because there are many more people than project groups. And so part of your final grade for the project, like you have, 10% was milestone 1, I can't remember how many percentage is milestone 2, there's a small percentage for your reviews, just completing your reviews. And the instructions for reviewing are down here. I can't actually make this bigger. I can. There you go. So it's very basic. This is what you're supposed to do. Essentially, you're going to score every project out of 60 based on these criterion here. This criteria: motivation, did they sufficiently motivate the problem, review of prior work, objectives, novelty, suitability, and description of the method. So, you're just going to give them some kind of score out of 10 for each of those. Please be nice and constructive. There's no point in being like negative to your classmates. It's not really going to help anybody. So if you think something can be improved, just say, be constructive and be nice about it. And what we're going to do with these scores is that we're going to take the top 12 scoring projects according to these scores, and then the TAs and I are going to look at them, and we're going to pick 6 of them so that at the end of the semester, those 6 present talks in the final project period, and the rest of you give posters. And the people who give talks just give a little bit of extra credit for giving a talk. So having a bad score in terms of peer review is not going to hurt your project grade at all. So you don't have to worry about somehow, this peer grading like hurting you. It can only help in the sense that if you get a bunch of good scores, then we'll look among those top 12 and pick 6. Okay, so that's going to be what happens with milestone 2. And make sure to do your reviews. I think we even gave you a due date for the reviews somewhere in the instructions. If you don't get the reviews back, then that's just going to kind of, disrupt the whole process. So make sure you get them back. I don't think it should be too much work for you. It's just a matter of, like reading a couple of milestones and doing some very basic scoring here. Any questions about that? Okay. So due on Friday. So just remember to submit them through EasyChair. So today we're going to cover coordinate descent. It relates in some way to what we talked about at the end of the last lecture, which is the Gauss-Seidel iterations for solving a linear system. So that we're going to say that's actually a special case of a more general method called coordinate descent. So a very quick recap of last time. So we talked about the basic cost associated with a bunch of operations that are common in optimization, but also just generally speaking in many applications of engineering, statistics, machine learning, this kind of stuff, and how there's a basic hierarchy of costs, and you should think about somehow things as getting more expensive. So vector-vector operations are cheap. They're linear in terms of the number of the dimension of the vector, and matrix vector multiplication is the next kind of more expensive class. It's on the order of n squared. Matrix-matrix multiplication is on the order of n cubed. And solving a linear system is actually the same in terms of, let's say, at least the rough complexity as multiplying two dense matrices. It's also n cubed. Operations with banded or sparse matrices are much cheaper. So banded, that is a kind of quantitative fact. We can say that the cost associated with, let's say, solving a linear system that has a bandwidth of k is nk squared. So that's going to be much, much smaller than n cubed if the bandwidth is small. Sparse matrices don't have a definitive worst-case complexity that we can cite that's much better, because it depends on the sparsity structure. But let's say empirically, you can do a lot better with sparse matrices. And you should think about it as being close to linear in practice. If you have like if you have only a linear number of elements in the matrix being non-zero, so if the sparsity S is on the order of n, then you should think about it as roughly being, you can do a linear time solve empirically. Okay, we don't have great, like I said, worst case bounds for it. We talked about two classes of approaches for linear systems that are based on two very different sets of ideas. The first were direct methods, and the two we talked about were QR and Cholesky. These are by no means the only direct matrix factorizations. There's several others. We talked about the fact that the QR requires a bit more memory and is a bit slower, but it's more stable. And the Cholesky is a bit faster and requires less memory, but it's less stable in the sense that let's say for solving a least squares problem, it's more affected by conditioning than a QR. In terms of, let's say possibility for numerical errors, that is. The other class of methods is called indirect, and these are more closely aligned with what you've learned so far in the course. These are iterative methods for solving a linear system, and maybe the most intuitive one is just to apply gradient descent to a particular loss function whose solution is the solution to the linear system you're looking for. So it's a particular quadratic loss function. And these have different properties than direct matrix factorization methods. They only approach the solution in the limit as the number of iterations approaches infinity. And they can be more efficient if the matrix is very large and sparse. And so the rough rule of thumb is that if the problem easily fits into memory, go with a direct method. If it doesn't, go with an indirect method. That's just a very rough classification. This is relevant to us, kind of knowing what methods we can use to solve linear systems, and when linear systems are hard or easy. It's a relevant thing to know for us in terms of optimization, because you might think about this guiding your choice of Newton versus first order. Okay, if you know that the Hessian is banded or the Hessian is sparse, and if you know that somehow it has a nice structure even, then that suggests that using Newton's method is a good idea, because the linear systems within Newton's method will be cheap and it'll converge quickly. If the Hessian is large and dense, then it's not so clear that it's a good idea to use Newton's method. Then it really depends on somehow with what stability you can solve these linear systems, how quickly you can solve them in practice. So knowing the details of this, like I said, is kind of a helpful thing for you to think about deciding between first and second order methods. Any questions about that before we move on to coordinate descent? Okay, so here's the outline for today. I'm going to talk about coordinate descent, give lots of examples, talk about some tricks that we use to implement coordinate descent quickly in practice. And then this stuff is just extra. This is actually quite a long lecture, but I don't really plan to get to all of it. The graphical lasso and the screening rules are just extra. They're just interesting things related to coordinate descent, and if we happen to get to them, great, and we probably won't get to all of it, and I might just ask you what you want to hear towards the end of the lecture. So let's try to motivate coordinate descent as a method. So far we've seen some pretty sophisticated methods. Probably the most sophisticated were the interior point methods we saw. And we're going to focus on a very simple technique in today's lecture that is surprisingly scalable and efficient for certain problems. Not for all problems, but for certain problems. And it's called coordinate descent, but probably more accurately, you might call it coordinate-wise minimization. So to motivate this algorithm, we're going to think about a particular question. And that question is as follows. If I give you a function, f, and it's both convex and differentiable, and suppose I tell you that you're looking at a point x such that if you were to move along any of the coordinate axes, f could not be made smaller. Okay, so if I start at x and I move, let's say, along any coordinate axis I, so I add a bit of, in the ith position, let's say delta to x, where delta is positive or negative, then for any choice of delta, I have the property that it looks worse in terms of the function value than I saw at x. So f of x plus delta ei is bigger than or equal to f of x for all delta and also for all I, for all coordinate directions. So the question is, does that imply that I have a global minimizer? Okay, so again, somehow you can think about it like I have some function, I tell you it's convex and smooth, and I'm at a point such that if I were to look to move along either of the coordinate axes, I can't make the function smaller. I only make it larger. Does that imply that I'm at the solution? What do you guys think? How many people think the answer is yes? And how about no? Okay. So the answer is yes for this problem. The proof is super simple, but it's, for those of you who voted no, don't feel bad because I think, it's a very slippery thing. We're going to see it's not true once we move differentiability. But with differentiability, okay, so the picture is somewhat like this, right? I have a smooth function. I drew the contours here. If you're at a point where you move, let's say, in this case, in the x direction or the y direction, you can't make the function smaller. That does imply that you're at a global optimizer, global minimizer, because for a smooth convex function, that's equivalent to the gradient being equal to 0. Okay, but the gradient by definition for a function that's differentiable is just the vector of partial derivatives, right? And each one of these is 0, because I've told you that if I were to try to optimize along that coordinate, I can't do any better, which by definition for univariate optimization means that this partial derivative is 0. Right? So just once again, being minimized along a coordinate axis implies that the partial derivative is 0 for that coordinate. Right? That's just univariate optimality. That's true for all coordinates, so that the gradient is 0, in which case I know I've minimized the function. Okay, I already gave the answer away. It's kind of a shame. I should have maybe been more suspenseful. I just said it wasn't true for not differentiable functions. So interestingly enough, once we keep convexity, but we remove differentiability, the answer is no. This is not sufficient. Okay? We could have a function that is minimized along every coordinate at a particular point, but is not globally minimized. And all we need to do to prove that that's not a sufficient condition is to come up with a counterexample. That's what I've done here. Okay, so here's my function. It's convex. Okay, it's not differentiable. In particular, it's not differentiable along the line, in this case, x1 equals x2, so the 45-degree line. And here are its contours. So you can think about it, it kind of roughly looks like a boat, okay, in 2 dimensions. And this non-differentiability is like the hull of the boat. And if I look at any point along the hull, like I just picked this point, for example, if I try to move, let's say in the x direction, I only make the function larger, because if you look carefully, I only visit more outer and outer contours. Right, so at this point, if I move to the right or to the left, I only visit contour levels that correspond to larger values of the function. So that's telling me that I can make the function smaller along the x-axis, starting here, and the same with the y-axis. As I move up or down, I only visit more outer and outer contours in terms of the level attained by the function. Okay, but I'm not at the global minimizer. The global minimizer in this case is just 0, 0. So I had to jointly move x1 and x2 in order to get there. I couldn't do it with any coordinate move. Okay, so that's kind of slippery, right? Because differentiability makes all the difference here. It's not convexity. I mean, convexity is playing an important role, but it's not sufficient just to have convexity. So, all right, the last question is, how about if I gave you a non-differentiable function, convex but not differentiable, but has a particular form? And that form is as follows. it's equal to g plus h, okay, where g is convex and differentiable, and h is convex but not differentiable. However, it's separable, which means that I can write it as the sum of hi xi, for the special form, right? This kind of looks like what we were doing with proximal gradient, but it's actually even more specific because I have a convex and differentiable function, and this one is convex and it's also separable, which means that h of x is equal to the sum over all I of hi of xi. Okay, so at this point you can guess the answer, right? Because it would be a weird motivation for the lecture if I somehow arrived at 2 no's in a row. So it turns out for these functions, it is sufficient to have minimized the function along every coordinate axis. Okay, and intuitively what you can think about what that does, that it takes all the non-differentiabilities and it aligns them with the coordinate axis. Okay, so if non-differentiabilities were the problem, if we've aligned them with the coordinate axis, then somehow we can escape that because we're talking about exact minimization along the coordinates. So we're never going to have to make a joint move in order to get to the global optimizer. So I've just rotated this picture here so that in this case actually we have non-differentiability along both the x1 and the x2 axes, but that's okay because it's never going to create this problem we saw here. Okay, the proof of this is actually, I think it's quite simple, but it's not entirely obvious. So let's go through the proof. So what I want to prove for such a function f, let's say, is that if I'm at a point x, which satisfies this coordinate-wise minimum, so if x is, let's say, a coordinate-wise minimum, which we defined to be what we wrote down previously, right? It satisfies this property. We're going to try to prove that the function is globally minimized at x. So we're going to try to prove that fy minus f of x is greater than or equal to 0 for all y. Okay, so the first thing we're going to do, okay, we're just going to write this in terms of its expansion in g and h. And now we're going to use the first order optimality condition for convexity on g, right, which says that g of y has to be bigger than or equal to the tangent line starting at x evaluated at y. Or in other words, g of y minus g of x has to be bigger than or equal to the gradient of g of x transpose y minus x. That's just the first order condition for convexity on g. Okay, and I'm going to just remember that h is separable. So I can write h of y minus h of x in terms of the difference between hi of yi and hi of xi summed up over all I. And now I'm just going to collect terms. So I'm going to just write the ith component of the gradient as the gradient sub I. So I'm just going to write this as one big sum, right? Just pull this inner product, write it as a sum and then put them all in one big sum. So this is just the ith partial derivative times yi minus xi. That's exactly what this is. And I have plus hi yi minus hi xi. And now I claim that actually every one of these terms in the sum is non-negative. And that's implied by the fact that I have a coordinate-wise minimum. So I claim that each one of these things is bigger than or equal to 0. And if that were true, then that we would have our f of y being bigger than or equal to f of x. And so why is that true? Let's just fix an I. Okay. So if x is a minimum along coordinate direction I, then we know that if I were to take the function f and I were to look at it along just that one coordinate, it has to be minimized there. So by subgradient optimality for that function project along that one dimension, I have that 0 has to be an element, right, of the subgradient of my function along direction I. But, okay, let's look at my function along direction I. If I look at f of x plus delta EI, right, that's just going to be equal to g of x plus delta EI plus h of x plus delta EI, right? And what are subgradients of this as, let's say, a function of delta? If I think about fixing x and just looking at that. So it's convex, so I can take the gradient of this part and the subgradient of this part. The gradient of this part along, or in fact, it's just the derivative because it's univariate, along the coordinate direction, the ith coordinate direction is exactly this. So it's the ith partial derivative. And remember, this h, right, I can write this as a sum, let's say over all j now, of h of xj, right, not equal to I, plus h of xi plus delta. So it's only the, this should say hi and hj. It's only the ith function that's being changed here, right? All these remain the same. So if I look at the subgradient, this is all a constant, right? I'm thinking about just taking the subgradient in the ith component direction, and I just get the subgradient of this function hi. So plus the subgradient of hi evaluated at xi. So this condition is exactly equivalent to f being minimized along the ith coordinate axis, right? Because I've just somehow restricted myself to a one-dimensional problem along that coordinate axis, and I've used subgradient optimality, and I just used the fact that somehow, you know, this was differentiable and they were convex, so I could split it up like this. So this condition is true, which tells us that actually the ith partial derivative is an element of the negative subgradient of hi of xi, right? Which in turn tells us that if I just use the definition, right, of a subgradient, it means that if I look at hi of any point yi, right, it's larger or equal to hi of xi plus the subgradient times yi minus xi. But the subgradient, I should write it maybe like this, the negative gradient is a subgradient of hi. I have the subgradient is just minus the ith partial derivative of g at x times yi minus xi. Right? And if I just rearrange this, I can see that actually this is saying that h of yi minus hi of xi plus the ith partial derivative times yi minus xi is bigger than or equal to 0, which is what I wanted. Right? That's exactly this term in the sum. So in other words, I've just shown that for any point y, f of y is bigger than or equal to f of x, because we've reduced it due to the nice separability condition as a sum of terms, each of which we know is non-negative because of the coordinate-wise minimization property. Okay, so that's the proof. Like I said, I don't think it's not very long, but it's also a bit subtle. And now we know that functions of this form, right? If I have smooth plus separable, all functions being convex, then it's sufficient to say I've minimized my function along every coordinate. And that inspires a method called coordinate descent, which is just repeatedly minimize out over each coordinate one at a time until I don't make any progress. At that point, I'm at a coordinate-wise minimum by construction, and for such a function, that's good enough. Right? That implies global optimality. So the method is just to fix an initial point, and let's say look at x1, fix components x2 through xn, and minimize my function f just over x1. Then to look at x2, fix components x1 and x3 through xn, minimize my function only over x2, and so on and so forth. Okay, and I do that for all the coordinates, and then I go back and I repeat. So we usually call for coordinate descent passing over the coordinates 1 through n, let's say a cycle, we call it a cycle, and these are the iterations. Every time I do a full cycle, that's one iteration. So an important note, okay, is that in this method, we're always using the most recent information possible. So this is why I've written it I've shown you what an arbitrary update looks like to the ith component, to xi. If you look at x1 through xi minus 1, okay, assuming we visit the coordinates in order 1 through n, I'm using the most recent value of those, right? So these are the values that I found in the earlier parts of the cycle, right? Because I'm denoting them by x1k to xi minus 1k. These ones I have not touched yet in my cycle, so this is the old value. If I were to plug in x1k minus 1 up to xi minus 1k minus 1, okay, that would not be using the most recent information possible. That would be using always the information from the previous cycle, and that would not converge. Okay, that would not be a method that we could run generically. Let me pause for questions. Okay, so this is actually quite an old method. People don't even know somehow what the first reference for this is, because it seems like such a natural method. But there's at least references in the 60s and the 70s that explicitly kind of refer to this method in papers. Most of the theory for coordinate descent is attributed to Paul Seng. So Paul Seng wrote a lot of papers about coordinate descent, and it shaped the foundations of this method kind of unilaterally, all by himself. And he has a nice paper in 2001 that proves that for any function of that form, separable, if you were to run this method, coordinate descent, and you were to find any limit point, so there was any point that was visited, let's say infinitely often in this coordinate descent sequence of iterates, then that must be a minimum of your function f. Okay, so if there's not a unique minimum, it could be kind of bouncing around between them, but any limit point would be a minimizer of f. And this paper actually is substantially broader than what I'm paraphrasing here. This paper applies to the case where this function g is not even convex. It's smooth, but it's not convex. And he actually proves that for such functions, you still get the property that coordinate descent will converge to a stationary point. And there's probably even more in it than that. So it's quite a broad paper. So some comments. The order in which we visit the coordinates is arbitrary. So I'm just writing down 1 through n. It could be any permutation of 1 through n. It could actually be I apply a random permutation of the coordinates and I pass over them in that order. And papers like Paul Seng's and other papers, they actually even say that it doesn't have to be cyclic or even permuted cyclic. You have to just visit each coordinate often enough. So, for example, sampling coordinates at random, completely at random, is itself okay, because you will, with high probability, visit each coordinate often enough. You can't just visit, let's say, coordinates 2 through k for many, many iterations and not touch the others. Or 2 through I or something for many iterations and not touch the others. That's not allowed, but anything that's close to cyclic is fine. Everywhere when I write xi, it does not have to be a single coordinate. It can be a block of coordinates. And the blocks can be arbitrarily sized. Okay, so I could have just some block decomposition of my optimization variable, and as long as I repeat this method, every step. The all-at-once update, we're using the information from the previous cycle, does not necessarily converge. The analogy for linear systems is exactly Jacobi versus Gauss-Seidel. So as I'll show you just in the next slide, this version of coordinate descent that we're describing for solving the linear system is exactly Gauss-Seidel. And the all-at-once scheme, where we use these having k minus 1 as a superscript, that's exactly Jacobi. Yeah, it's a question.
How is all at once different from a block that's all coordinates?
Well, so for a block that's all the coordinates, this is not a method that we really know of, right? So for a block that's all the coordinates, what this is saying is that you can't optimize every coordinate individually. So the comment about blocks meant that if I had blocks of size 2, let's say, then every one of these would be an exact minimization over 2 variables. Or if I have blocks of size 5, then I'm going to be performing this exact minimization over those 5 variables. So the problem is that if I have all of the coordinates, okay, of course, I mean, the method that somehow exactly minimizes over all of those variables is a valid way to minimize the function, right? That would just give me the solution in one step, but it's not computable or something like that. So if you have blocks, you have to optimize out over the blocks exactly. Did that answer your question? Yeah. Other questions? Okay. So let's go through maybe the simplest example, which is solving a linear system, which is equivalent to performing linear regression. So we're going to just look at standard least squares. We're going to say which we know is equivalent to solving the normal equations, right? It's equivalent to solving this linear system. X transpose X beta equals X transpose Y. And we're going to apply coordinate descent to this criterion, and we're going to see that it's exactly Gauss-Seidel for this linear system. It's the same method. Well, I guess we can get that later. So, all right, let's do that. Let's think about minimizing out over beta I. So I'm going to take blocks of size 1, so truly coordinates. In fact, all my examples will just be really coordinates. And I'm going to keep all the other beta j's as fixed in this calculation. Okay, so minimizing out, let's say, over beta I is equivalent to taking the ith partial derivative and setting it equal to 0. Right? Because this function is convex and smooth. Just to remind you, here's what it is. I actually like debris, so maybe we open it back up at halftime. But I see. Okay, no problem. Okay, so this is my function. I'm taking the ith partial derivative and setting it equal to 0. That'll be equivalent to minimizing out over beta I. And that just gives me 0 equals xi transpose y minus x beta. Okay, and I'm going to write x beta as xi beta I minus x minus I beta minus I. So by this I mean I just take the ith column of x and I multiply it by beta I, and this means all but the ith column of x and I multiply by all but the ith component of beta. Just writing out x beta in terms of the ith column times beta I and all the other columns times all the other coefficients. And remember, I'm considering these fixed here, right? So this is like a really simple calculation now. I have to just find the value of beta I that makes this 0. And so this is the same as saying xi transpose xi beta I, right, is equal to xi transpose y minus x minus I beta minus I. Right, or in other words, beta I is equal to xi transpose the residual without beta I, which we also sometimes call the ith partial residual, divided by xi transpose xi. Okay, so this is exactly the Gauss-Seidel update for this linear system. Right, what it looked like was let's call this A. Let's call this B. I just took B minus the matrix product of A with all the other variables, which is this, divided by AI, the ith diagonal element of A, which is just xi transpose xi. So this is equivalent to Gauss-Seidel. for this system. Okay, and if I just repeat this, let's say for I equals 1 through n, I equals 1 through n, I equals 1 through n, that's just cyclic coordinate descent. So I showed you already last time, actually, a comparison between Gauss-Seidel gradient descent and conjugate gradient for linear systems. Okay, and I added two more things to this picture, actually. So let me first just point out to you, this is the same experimental setup at the end of last time. I'm just doing linear regression on 100 random instances, and I have 100 observations and 20 features. So I'm just trying to show you kind of the gross behavior of convergence here. In red are the coordinate descent criterion as functions of, this is how it decreases the criterion as functions of the iteration. And the dark red shows the average curve. In blue is conjugate gradient, so we can see that they're both converging faster than the other methods. And they're converging about the same rate. It looks like conjugate gradient does a little bit better at getting very high accuracy solutions. In green was gradient descent. Okay, this is what we saw last time. Now, for this problem, for linear systems, okay, it's just a quadratic. And so for gradient descent and for conjugate gradient, we could actually do exact step size optimization. I could find at every iteration the exactly optimal step size. Right? We did that calculation, or at least I mentioned what that was last time. It's a special case, it's a very special case in which that's true for gradient descent. We can do exact step size optimization. So that's explains these three. Okay. These two are what happens if we apply gradient descent and accelerated gradient descent, but with our standard rule for the step sizes, which is that we take them as big as 1 over the Lipschitz constant. Okay, and backtracking would be the same here. I'm not showing the backtracking curves because they don't look really any different. 1 over the Lipschitz constant of the gradient is kind of, in terms of our standard theory for gradient descent, the largest we can take the step size. Okay, so it's not adaptive. It's not adapting at each iteration. Backtracking would, but it wouldn't be any better. Exact step sizes make a much bigger difference in this problem. Because here's gradient descent. It's in blue. Accelerated gradient descent we see it's in this purple. It's not a descent method, so I guess I should call it accelerated gradient method. It has a little bit of wiggles. But they're clearly inferior in this case to coordinate descent and conjugate gradient. So why am I showing these two? It's because for the purposes of this lecture, the most relevant comparison is actually the red to something like the purple and the blue. Because as we move forward past least squares, as we move forward past the linear system solves, coordinate descent is a method we can apply. Conjugate gradient isn't. And we can't use exact step sizes in general, so we should be comparing coordinate descent to standard gradient descent or accelerated gradient descent, right, with the standard choices of step sizes. So there's a big difference between, let's say, red and blue and purple here. That's the point I'm trying to make. Any questions? Yeah. So exact for gradient descent. So in this problem, a gradient descent looks like this. Okay, so it's beta minus the step size times the negative gradient. And okay, in gradient descent, we can set t to be, for this linear system problem, it's the exactly optimal, let's say, value of the step size, such that the criterion is minimized if we tried to move in this direction. So in general, we can't perform this calculation, but because f is a quadratic, it's just this guy up here. Okay, this is something we can compute. And I'm just going to venture this as a guess from memory, but you should check to make sure that I didn't do this wrong by looking at the previous set of slides, where R is the residual and A is x transpose x. So I think that's right, but in any case, this is just a quadratic, right? So we can perform that univariate minimization. So it's something that looks like this. When f is not a quadratic, so in most cases of interest, let's say for general optimization, not just solving linear systems, this is not possible. So we do things like backtracking, or we just find the Lipschitz constant and take one of the Lipschitz constant as the step size, which is these guys up here. Other questions? Yeah.
How do you count an iteration for coordinate descent? Is that a cycle?
Yeah, good question. That's a full cycle over all the coordinates.
Because that feels like an unfair comparison to grade.
It's a very prescient thing you ask, because that's my next slide. So I think, yeah, if you just look at it maybe at first pass, it does feel like it's perhaps doing more work than gradient descent. So maybe it's unfair to say this n times is equivalent to one step of gradient descent, which is this. Okay, but where we can make a coordinate descent really efficient in practice is by taking these updates very carefully. And it turns out that if we're kind of careful about the way we perform these updates, one full cycle is the same cost as gradient descent. They're going to have the same complexity here, and that's just going to be order n times p. Okay, so first of all, it should be clear, at least now from our last lecture, that gradient descent costs order np flops, right? Because the dominant cost is just doing a matrix multiplication of x transpose times y and x times beta, right? Those are that's each of those cost order np. And in coordinate descent, okay, this is one coordinate update. It's exactly what we derived here on the notes. I'm going to write that as the following. Xi transpose the full residual, where r is what I wrote down here. It's y minus x beta, divided by, I'm just writing xi transpose xi as the norm of xi squared. That's not important. But I'm adding in beta I. Because, okay, why is that true? Right? If I look at xi transpose the full residual divided by xi transpose xi, right? And I add beta I. This is the old value of beta I, the one that I had in the previous cycle. Then this is equal to xi transpose y minus x minus I beta minus I minus xi beta I divided by xi transpose xi plus beta I. Right, I'm just writing the residual y minus x beta as I'm separating out into the contribution of beta I and all the others. And okay, if you look at what happens to beta I now, I just have xi transpose xi beta I over xi transpose xi, and that cancels out with this beta I. So this should be exactly as I had before. Okay, so I'm just saying this is an alternative way to write the same updates, where you should interpret this as the old value of beta I. And now we can see that somehow, if we're careful, we can perform each coordinate update in exactly order n flops. And since we have p of them to do, so here beta is p-dimensional, so we cycle over coordinates 1 through p. Then an entire cycle should cost order np flops. Okay, so why is each coordinate update costing just a linear number of flops? That's because if we just keep track of the residual, okay, then to update the residual from one, let's say, coordinate update to the other, we have to just add in the old value of xi beta I and subtract off the new value of xi beta I. So that's the only thing that differed between, the update before and after I touched coordinate I, right? And that I can do in order n time. That's just adding a vector of length n and subtracting a vector of length n to r, which I'm storing. And so if I've updated this in order n time, then this calculation, right, xi transpose r, is just an inner product that takes order n time. This is a vector, that's a vector. And this is just a scalar. So this is just a constant number of flops from this addition. So that means somehow this whole update is just order n after updating r cleverly. And I'm doing p of them, so there's exactly order np cost to one cycle. So it's the same as gradient descent. Yeah.
Just to compare the rates, in terms of like the number of iterations, both of them are like log of 1 by epsilon, right? Like all of the results in the previous plot. So is it just the constants that are differing, that's why you get the behavior?
So for this problem, yes. For linear systems, yes. But remember, there's a big difference somehow in the constants. It's a matter of conditioning versus square root. It's the condition number versus square root of the condition number between conjugate gradient and gradient. And that can be a very big difference somehow in practice. And what the maybe slightly surprising about this example was that I was not trying to be malicious in any way with conditioning. These were standard Gaussian entries in my feature matrix. So this is like the nicest condition problem you can imagine, probably. The nicest random problem that's conditioned well, let's say. And it still makes a difference here.
Why it's not similar to the gradient example?
It's not hurting you. I mean, I think what's happening is that somehow, in most iterations, acceleration for that problem instance is better than gradient descent for that problem instance. And some of them are about the same. I mean, there are some instances where somehow I think like there's overlap, but I think in most of them it's a little better. It's not. It doesn't look like a huge difference in this problem, which, yeah. Other questions? Yeah.
This order entry thing is specific to least squares, right?
So not really, actually. So we're gonna do now the lasso, which is I think a substantially harder problem, obviously, and we're going to see it's the same. So for most problems in which coordinate descent is applied, they're applied because you can do these quick updates. So there's quite a number of them, but it's a good question. Okay, so all good questions. So let's jump into the lasso, and then I think we can take a break. The lasso is a small change to the criterion, but a big change to the difficulty. Obviously, we've seen several algorithms for the lasso so far. And we're going to just look at coordinate descent now. Okay, so if I were to minimize out over beta I, okay, the only difference is that where I had, let's say, a gradient here, I should be taking a subgradient with respect to beta I of the criterion. And, okay, this is exactly as we had before. This is just the gradient of the least squares part of the loss. Right? That's exactly as we had before. And this is the subgradient of the non-smooth part, but I'm only taking the subgradient with respect to beta I, right? So it's just lambda times Si, where Si is in the subdifferential of the absolute value of beta I. Okay, so it's 1 when beta I is positive, it's negative 1 when beta I is negative, and it's anything between -1 and 1 when beta I is 0. So we already done this calculation when we talked about subgradients and proximal gradient. We've already done the calculation as to what, let's say, value of beta, or beta I in this case, will satisfy an equation like this, where Si is the subgradient of the absolute value of beta I. And the answer is soft thresholding. That's the answer. Okay, so you can go back to that when we talked about subgradients, and you can look at somehow the arguments for how we derived the soft thresholding operator. You can see that they stem from exactly, it was really exactly this problem. The only difference here is that we have a scalar multiplying beta I, whereas before we didn't. Right? So we had, if you look back, we didn't. So we could divide by that. That's fine. Divide everywhere by xi transpose xi. It'll make it look like our previous version of the problem. Okay, but so the answer is soft threshold by an amount lambda over xi transpose xi. That comes from dividing, let's say, everywhere by xi transpose xi, this thing, divided by xi transpose xi. So I think it's very intuitive, because without the L1 penalty, okay, this was the coordinate update. It was exactly that. With the L1 penalty, we perform the same update, and then we either set it to 0, or we subtract lambda, or we add lambda to it, depending on whether this is larger or smaller than this constant, lambda over the norm of xi squared. Okay, so you can see why in the lossless solution we're getting sparsity. It's because we're taking the least squares coordinate updates, right, which just take the inner product of xi with the partial residual, excluding beta I. And for those of us that are familiar with kind of various formulations of regression, this is just the univariate regression, right, of the ith partial residual on xi. That's the coefficient from that univariate regression. And we're either setting it to 0 or making it closer to 0. That's what the soft thresholding is doing. Okay, so looping through that for I equals 1 to p, I equals 1 to p, I equals 1 to p, etc. That's coordinate descent. So for the same reason as this one, okay, it's going to be order np to do one full cycle. Because the only difference now between least squares and the lasso is this soft thresholding application. But that can be applied in constant time, right? That's just comparing what we already knew how to compute quickly to this, and then subtracting off lambda, adding lambda, or setting it equal to 0. So it's again order np for one cycle. And here's a comparison now that I think is a more useful comparison than the linear regression case, because now we don't have algorithms like conjugate gradient or gradient descent with exact step size optimization for the lasso. Right? We have proximal gradient. That was, in some sense, the best method we learned so far in this class for the lasso, and is one of the more popular approaches for L1 penalized problems. And we can see that coordinate descent is getting a much faster convergence empirically here. Okay, I have proximal gradient in green, accelerated proximal gradient in blue, and coordinate descent in red. Every method for one iteration takes order np flops, and they converge at quite different practical rates. Okay, so let's take a quick break, and then we'll come back and I'll talk about a few more problems and then some implementation tricks.
Try again with the door, but when it was picking up like
I
that,
see.
you can hear like
see.
it's making all kind of noise.
I'm whatever you think. I'm good with whatever.
But if it starts singing again, I'll just walk down again. It was
Okay.
just picking up really strong at that point.
Yeah.
Jacobi, do you have any sense of like when Jacobi is guaranteed to converge?
Yeah.
Like in this problem.
Yeah, there's. So I have two answers for that. One is that there are, if you look at the Jacobi method itself, it's in a particular class of methods called splitting methods. So both Gauss-Seidel and Jacobi are in a class of methods called splitting methods. Splitting methods, if you kind of look at the formulation of a splitting method, there's a general theorem that says that if the spectral radius of the matrix operator in a splitting method is strictly less than 1, then it's a contraction maximum you're applying, and so it's going to converge. So that gives you a convergence criterion for Jacobi,
I see.
but it essentially is a condition that never holds in practice. Like for some matrices it will, so for some linear systems it converges,
Oh, I see.
but for
like,
randomly general linear systems they don't
almost
satisfy that.
never works. I see.
Okay, the other answer is that modified Jacobi iterations will converge. So
So it's like in between Jacobi and then Gauss-Seidel?
well, it's something like, if you try to make somehow, how do I say this? Imagine taking all of the coordinate updates and trying to move them to their Jacobi iterates, but not moving each one of them all the way. Moving each one some fraction of the way. So I actually can perform everything in parallel,
Oh,
but then instead of updating all the coordinates exactly to where I would have. Okay, guys, let's do a few more examples. These ones I'm going to go through less quickly more quickly, less carefully, because I wanted to kind of show you how you derive these updates for some basic problems, and then I think you could just kind of go forth and do it on others. So I'm just going to portray the fact that you can do this on other problems without giving kind of so much of the details. So if I have a box-constrained quadratic program, then it turns out that this is not a trivial problem to solve. If I have quadratic program subject to box constraints, and you can solve that with coordinate descent quite efficiently. Okay, and in this case, the coordinate updates are dominated by the cost of truncating rather than soft thresholding, which is kind of very similar operator. But there's still going to be linear time in the dimension of the optimization variable, each coordinate update. Okay, so it's still a very efficient problem to solve with coordinate descent. Similar to that, okay, where do we see box-constrained QPs? A box-constrained QP that's something that actually is very kind of a very common problem you'll encounter in practice is the SVM dual. Okay, so the SVM dual is like a box-constrained QP, but it has one additional complication, which is has a linear equality constraint as well. Okay, so if you're unfamiliar with this, then go back and look at the duality lecture where we derive the dual of the SVM. You can see where this comes from. This is just like a standard linear SVM, or if it's a kernel SVM, I just replace this by the kernel matrix, so it's no less general. And I can see that the dual variable is alpha. This is a quadratic, and the constraints I have on alpha is that alpha is between 0 and c, and every coordinate, and alpha transpose y is 0. This is, like I said, this linear equality constraint. So if we look at this, all right, so actually first I wanted to explain to you, this is the easier problem, why this fits into our framework. I kind of did not do that, so let me take a minute to do that. I can write this constraint as an indicator function. It's the indicator function that x is between L and U, right, coordinate-wise, where L and U are two vectors that determine my lower and upper bounds. And because this is a box constraint, I can write this as the sum over all I, that xi is between Li and Ui. And so this is my smooth part, and if I add this to my criterion instead of writing the constraints, then this is my non-smooth part, and it's separable. Right? It's the sum of some function of xi alone. So that's why it fits into our framework. That's why coordinate descent can be applied and why it converges. Okay, the same is almost true in the SVM dual, right? All of this part up here would follow the same logic. I just write this as G. I write this as an indicator, and then I write that as a sum of hi of alpha I, where alpha I has to be between 0 and c for every I. But this thing here, okay, this constraint, alpha transpose y equals 0, that is not something we can turn into something that's in the criterion that's separable. Right? We can put that as an indicator in the criterion, but then it actually is a non-smooth function that tangles all the variables together. So this falls strictly outside of the scope of the class that we just described. But nonetheless, coordinate descent can be applied, and there's one of the earliest and kind of, at the time, most used algorithms for SVM was doing exactly that. And it just requires a different analysis because it doesn't fall into the standard framework. So the analysis for the SVM dual is different than what you'd see in kind of the classic Paul Sang optimization papers. So for SVMs, they call it sequential minimal optimization, but it's just coordinate descent with blocks of size 2. Okay, it's done with blocks of size 2. And instead of cycling, it chooses the next block greedily. So I didn't mention that as a rule. It turns out that instead of choosing to cycle over the coordinates, in some cases, you can use heuristics to choose the next coordinate greedily, and those will still converge. Okay, and just in case you're curious, in the case of linear systems, that algorithm is called Gauss-Southwell. So it's another variant of the Gauss-Seidel algorithm that chooses the next coordinate greedily. So I'm not really going to go into details. I'll just maybe say as a picture, what we're trying to do is we're trying to optimize over alpha 1 and over alpha 2. You know they have to be between 0 and c. So each subproblem looks at a box, right, of side length c. And we have some linear constraint that we have to lie along. Right? This is determined by the constraint alpha transpose y equals 0. That's some linear constraint on alpha 1 and alpha 2. Tells me I have to lie on some line. And so the sequential minimal optimization algorithm, it optimizes the quadratic over this line segment. That's exactly what its subproblem does. And it's no longer the most efficient coordinate descent approach for SVMs. There have been several that have been developed. A more recent one is this paper by Shea, which is it's a very efficient algorithm for SVMs. Okay, so let me give you a little bit of the history because I think it's interesting, and then we're going to say a bit about conversions, and if we have time, I'll talk about probably either the graphical lasso or screening rules. So its history and optimization is also kind of not clear, but as I said, I think there are papers in the 60s and the 70s that have studied it. In optimization, for a long time, people considered coordinate descent as kind of like a not interesting method. It was too simple. Somehow they didn't think that there were enough problems that you could solve with coordinate descent to make it interesting, because people were more interested in kind of, at the time, in the 70s, 80s, 90s, in developing interior point methods for solving very generic convex problems. Right? That was the main direction that the field was moving in. So there's a lot of effort put into those interior point methods. And coordinate descent is kind of ignored. It was thought of as like, you teach your students it, but you tell your students never to use it because it's, it's like a little toy method that is interesting. So in statistics and machine learning, the idea actually appeared a few times before it caught on. So in 1998, Wenjiang Fu had a master's thesis where he wrote down in his master's thesis this algorithm for the lasso. And for reasons that kind of are inexplicable, it was completely ignored for 10 years. People didn't even pay attention to it, even though it was published. And again, in 2004, some applied mathematicians, so Ingrid Debauches is a very famous applied mathematician, has it in her paper, but it was pretty much ignored. Okay, and these are describing essentially this algorithm for the lasso that I wrote down here. So this is a very useful algorithm for the lasso. It was around for a while, but people didn't pay attention to it. And then in 2007, there were 3 papers that came out at the same time, pretty much, that all said, hey, look, we have this algorithm for the lasso that's coordinate descent. And that really kind of caused a resurgence of interest in it in statistics and machine learning, and then in turn in optimization. So now it's kind of been revived, or maybe it was never really that popular, so it's been revitalized in optimization, and people are interested in it again. Anecdotally, let me just say that, so the paper that's most cited and most popular is this one, Friedman, Hastie, and Tibshirani. This is my father. Wenjiang Fu was his student, so it's especially shameful that he didn't help kind of push this to the spotlight. But the reason is, and this is not written down anywhere, is that these authors, so Hastie, Tibshirani, and Friedman, and many other authors, when these papers were out, they were implementing the Jacobi version of these algorithms. So they weren't distinguishing between the one at a time versus the all at once updates. So they were implementing them incorrectly, they weren't converging, and it was actually somehow this distinction that was not appreciated for a long time. And that's the reason why somehow it never caught on. So it's also kind of extra reason to be kind of extra careful about stating that you really have to do the coordinate updates one at a time. Always use the most recent information. So why is it used today? I think that there's maybe 2 reasons. The first, that it's very simple and it's easy to implement. Okay, so this implementation, let's say for the lasso, it maybe is like 10 lines of code. You have to just be a little careful updating the residuals. So it's a very simple and easy thing to implement. It's very portable. And if you perform the implementation carefully, and especially if you use a lot of tricks, which I'll describe, they can achieve state-of-the-art for the problems in which it's applicable. Okay, it doesn't apply to every problem. In fact, if you look carefully, the commonality in all of our problems so far we've talked about has been quadratic plus something separable. So that is really the situation in which you should be looking to apply coordinate descent, because the subproblems, if you have a nice enough separable penalty, you can solve exactly. The moment you have something that's smooth but not quadratic plus separable, you have to be lucky to get a coordinate update that can be done exactly. Okay, so some examples are lasso, generalized linear models with L1 penalties. But for these problems, as I said, or maybe as Zico hopefully highlighted when we talked about proximal Newton, the step we do is we first take the, like say, logistic loss, and we use proximal Newton to turn it into something that's quadratic. And then we apply coordinate descent for that inner problem. And that is a very efficient algorithm. So it's really, coordinate descent is the workhorse, let's say, for the logistic lasso or any generalized linear model plus the lasso. It doesn't apply directly to the criterion, but it applies after proximal Newton. SVMs, it's still very popular for them. The group lasso, the graphical lasso, it is the main algorithm, or the most efficient algorithm at this point for the graphical lasso. Additive models, matrix completion, even non-convex problems, there's a lot of work on coordinate descent for these problems. So let me tell you about some implementation tricks, and then I'll talk quickly about convergence guarantees. And then we may actually not have time to do the graphical lasso. We'll see. So this is why, let's say, coordinate descent is so efficient in practice. It's because not only do we have efficient updates coordinate to coordinate, it's because we also have other tricks that we use along with those to make the algorithm efficient. So there's typically a strategy called pathwise coordinate descent that's used for the lasso and related problems. And you can think about there as being two loops, an outer loop and an inner loop. The outer loop computes the solution. This is just warm start, so you're already familiar with this. Choose a sequence of lambda values from large to small, okay? And optimize over, let's say, the largest lambda value first for the solution. Use that to warm start the second largest lambda value, and so on, okay? And the fact that we're starting at a large lambda value, moving down to a small lambda value is actually very important for coordinate descent, which the reason for that I'll mention, hopefully will be clear once we talk about the inner loop. Okay, so this is just warm starting, but making sure we start with the sparsest solutions first and move down to the densest solutions. And the inner loop, okay, once we're at a particular value of lambda, what we do is we look at the KKT conditions for our problem. Okay, let's suppose our problem is the lasso. And the KKT conditions looks like this. And so on, right? And I perform one full cycle of coordinate updates. Okay, so here are the KKT conditions. I perform one full cycle of coordinate updates, so that just cost order NP flops, right? And I look at the betas that survived, that were not set to 0. Okay, and that's why this is efficient when you're expecting a sparse solution, because many of the betas will be set to 0 in that initial pass. So I just grab the betas that were not set to 0 by the soft thresholding operator in that initial pass, and I run coordinate descent on that subset, so potentially much smaller than P. So this is called an active set optimization. Once that converges, I go back to the KKT conditions and I check them. If they have passed, then I'm done. If they haven't passed, then there'll be some of them that are violated. Like, let's suppose the active set did not include coordinate 2. Okay, then this condition will be violated, and I have to add coordinate 2 to the active set, and all the other ones that for which the KKT conditions were violated, and then I just iterate over that slightly larger active set until convergence. Okay, after that converges, I go back to the KKT conditions, I check them. If anything has been missed, I add it to the active set, iterate till convergence, and so on and so forth. And at some point, I take a pass over the KKT conditions, and they'll be met. So this is called active set optimization. This is what we do in the inner loop. And now you can kind of see why, if I'm expecting a sparse solution, this is going to be very efficient, because I'll be only operating on a very small subset of the coordinates at this point. Right? That first pass over the coordinates in coordinate descent will set a lot of them to 0. And the rough idea is that somehow if we start at a large value of lambda, a very large value of lambda, this will converge very quickly. And then due to kind of continuity of the solution as a function of lambda, if I move to a slightly smaller value of lambda, I'm already close to the solution, so I should be converging quickly, and so on and so forth. So this plus screening rules, which I will not have time to go to, but you saw actually for SVM on your homework. So for the lasso, they're similar. This plus screening rules are really what sets coordinate descent apart in terms of practical efficiency. And this strategy is so efficient that even if you wanted the solution at one value of lambda, suppose you said you only cared about the solution at lambda equals 2, okay, which was, let's say, relatively small in terms of the spectrum of lambda that gave you, sparse to dense solutions. It's still more efficient, maybe surprisingly, to start at a large value of lambda and do warm starts down to lambda equals 2, as to running coordinate descent directly at a small value of lambda. So even if you don't care about the solutions at larger values of lambda, software for coordinate descent for the lasso will still do that because it's actually more efficient. That's just maybe emphasis for how important this warm start plus active set trick actually is. Okay, so the software that most everybody uses is written in Fortran. It's called Glimnet, and it's linked to a bunch of different major languages. Okay, let me quickly talk about a slightly different version of coordinate descent, and then convergence guarantees, and then I think that's all we have time for. So there's another version of coordinate descent, which is maybe important for me to point out, which is a much more widely applicable version of coordinate descent, in which instead of just taking the exact minimum along every coordinate, I take a gradient step with respect to that coordinate, or a proximal gradient step. So this is much more widely applicable than exact coordinate descent, because we don't have to be in the case where we kind of know the exact form of those coordinate-wise minima. So let's say if f is smooth, if I just take a step in the direction of the ith partial derivative of f, so this is like a gradient step but restricted to the ith direction, and I cycle that 1 through n, that's called coordinate gradient descent. Okay? And if I have, let's say, smooth plus separable, and I take a step in the direction of the ith partial derivative of g, and then apply the proximal operator of hi, that's called coordinate proximal gradient descent. So the only difference between gradient descent and proximal gradient descent in these versions is that these are applying those gradient steps, or those proximal gradient steps, along each coordinate one at a time, rather than on all of the batch of coordinates. Okay? And it turns out that when g is quadratic, this and exact coordinate descent are the same, as long as you choose the step sizes properly. And that's going to be that's a question that's on your homework. It's not a very difficult question. It just turns out that if you have a quadratic, then you can choose the step sizes to make this equal to the exact minimum along that coordinate. All right, so it's worth pointing out these variants because they're much more widely applicable. So let me tell you a bit about the convergence analyses, and then we'll quit. And either we'll just skip the graphical lasso stuff, which is fine because it was completely additional, or if you really want to hear it, we can do it next time. Okay, so theory for coordinate descent moves very quickly. It seems like there's new papers coming out really every year. And pretty much every combination of the following cases, I think, has been analyzed. So you can find a paper on every combination. So are you applying coordinate descent? Are you applying proximal coordinate gradient descent? Those are actually different, and they have different behaviors. For quadratics, if you choose the step sizes properly, they're the same, like I said, but in general, they'll be different. Are you using the cyclic rule, which is the hardest to analyze, by the way? It's the same reason why, for example, it's much easier to analyze stochastic gradient descent than taking the first gradient, the first data point to dictate the gradient, etc. It's just easier to analyze randomized algorithms. So the cyclic rule is in some sense, is the most popular in practice, and it's also the hardest to analyze. Permuted cyclic, which is easier to analyze, but still not that easy. Greedy, which is analyzable for some simple cases. Or random. So random is actually the easiest to analyze, again, for reasons that maybe are intuitive, but it's not as popular in practice. So just picking the coordinates at random at which to make updates on. So roughly speaking, the results are similar to proximal gradient. Okay? In that under standard conditions, you get standard rates. So for a function with Lipschitz gradient, you expect a sublinear rate. For a function with a Lipschitz gradient and a strongly convex, you expect a linear rate, etc. But I feel, honestly, that the state of the literature is a bit disappointing, because what we see in practice is that these perform much better than proximal gradient for the problems in which they apply. Okay, and the theory is not really revealing that. The theory is saying that you get results that are similar to proximal gradient, and in fact, it's not even similar but favorable. It's similar but worse, because most of the theory, okay, for coordinate descent establishes something like a linear rate or a sublinear rate, but has worse constants than you get for proximal gradient. So according to the theory, we should think it would perform a little worse in practice, but actually it's performing better. So there are some references here that I put down. Stephen Wright has actually this is the same Stephen Wright who has a whole book on interior point methods. He has a nice monograph on coordinate descent. It's like a very good resource for a kind of general purpose methodology and theory. But I think there still is not somehow like a unified analysis that really does this method justice. And I'll maybe just leave it at saying that the theory in these papers is much more difficult than the theory for proximal gradient. I mean, proximal gradient we did in the homework. We did gradient descent on the homework. Those are kind of standard analyses. The theory here is much more difficult. Okay. I don't think it's worth like massacring the graphical lasso in a few minutes, so I think I'll just call it there. And next time we'll either just start with dual methods or we'll pick up with the graphical lasso. So I'll see you guys on Monday.